how wonderful it is to be a faculty member working with graduate students. It is oftentimes the case when you're working on a PhD or you're working in a lab, you encounter all the difficulties, the getting of the grants, the publishing of the papers, but it's actually wonderful oftentimes too, and sometimes that isn't said explicitly, and so I wanted to share that. Tone is the 9th PhD student I've worked with to get to this point, and he is the most wonderful PhD student I've worked with. And I want to not just tell you that, I want to give you a couple examples of why that's true. I walked by the lab one time, and I saw this sign on the window. It wasn't very well written. It said, "Bike rentals." Talk to Tone, bike rentals. I didn't think very much of it. I walked by the lab a number of months later, and the sign had gotten a lot nicer. And I go, well, I better check in. What does this sign mean? Tone, what's the sign mean? He goes, oh, well, when I came to Stanford, I didn't have any experience as an entrepreneur. And so I decided to take a course over at the business school in entrepreneurship. And as part of that experience, I decided to start a company so I could learn how to be an entrepreneur. And I've started a peer-to-peer bike rental company here on campus. I go, wow, that's fantastic. That's just awesome. Who would have thought? Now, about a year later, I got a heads up from Sandy Meyer, who is one of the top administrators in the School of Engineering. And Sandy and I had been working together closely on the new building project, so we knew each other. And she said, out of courtesy, I'm just going to let you know you're going to get an email from somebody I'd never heard of who works with the provost and might be a lawyer, and has to do with Tone. Well, what's this? Well, Tone's company had become so successful that they had, you had a team bigger than the lab. They had a team of employees that were shuttling entire wagons of bicycles to this crowdsource. It was very successful. And I said, well, you're going to get this email. And this email came in, and it came down pretty hard. It was like, you're creating liability, and you don't have permission to operate a business on campus, and you shouldn't be operating a business out of the laboratory. And Tone's response, wow, it was really wonderful. So don't worry, I'm incorporated and registered with the state of California. We have liability numbers over here and there, and I'm working all off campus. This has nothing to do with on-campus business. That's example number one. Example number two is a shorter example. I got an email from Tone. I think it was on your birthday. And I was one of many people who got this email, and it was an email of thanks. It was an email he had sent to everybody who had had an impact on him in the previous year. Thanking him, thanking them, thanking us. I just had never gotten anything like that. It was amazing. Now, apropos what we're about to hear about, when Tone arrived in the lab, I think you had worked with Eric Winfrey at Caltech, and you couldn't do anything experimentally. But you were a really good thinker and a really, really good theorist, and you started out with a whole bunch of modeling and computational approaches and whatnot. But from that beginning, you shifted over, and you didn't throw out all of that good thinking and skills, and you became an experimentalist. And so Tone has really been this amazing person to watch and work with, become holistic in approaching bioengineering. Thank you so much.
So thank you, Drew, and thank you everyone for coming. So I hope this will be entertaining. About 4 decades ago, the birth of genetic engineering allowed us to directly manipulate DNA instead of relying on mutations and good traits that are available in nature. Since then, the cost and the time that required for building pieces of DNA have decreased by orders of magnitude. For example, these days it's possible to build the entire genome of a small microbe from scratch. Whenever we talk about building or engineering living things, what we do care about is at the level of phenotypes. Basically how this living thing looks and behaves and produces things that we care about. But the thing that we build and swap around is at this level of the sequence. So soon, we'll be able to build any sequence that we like. But the bigger question is going to be what sequence to build to get to the phenotype that we want. The sequence encode for different kind of function. Let's say gene, they encode for different pigments or enzymes. And complex phenotypes arise when these genes interact to one another in a big network. This ensures that the levels and the timing of gene expression is okay. The product from one gene can control the expression of the other genes, and this can be organized into something that functions like a simple logic. For example, you may have a gene that can only be turned on when two other genes turn on. So you have something that functions like an AND gate. Or a group of genes that take turns switching their state that function like an oscillator. About 10 years ago, people start to recreate those kind of functional modules that you see in the lab, inside the cell. So people build the logic gates, or the memory, the oscillators, the cascade. So many people back then start to believe that soon we'll be able to put these functional modules together to build anything that's complicated and do something useful that we like. Yeah? Now, unfortunately, that didn't really happen. So what you see here is the plot that shows the complexity of the published synthetic circuit, synthetic gene functions, as a function of about time, about 10 years. And you see here that the complexity that they measure as a number of components start to kind of later off. Okay. When we have these functional modules, synthetic functional modules built inside the cell, sometimes we have to think of it as a device family, that we can just put them together into something that's working right away, the way that we put device family together on the circuit electronics. However, that doesn't seem to be the case in biology. We have this thing, this tiny thing that's packed with a bunch of molecules. There's no clear separation between different components, so they're prone to undesirable cross-interactions. The things that we call parts or device sometimes doesn't operate reliably, and sometimes it's not even well characterized. And the system level rules and ways to put things together are not well established yet. So my work here, we start from the high-level equation of what it is like to try to put something very complicated